In the low energy and low frequency part of the spectrum, the behaviour of electromagnetic radiation can be best described as waves. Take, for instance, a wire with a single free charge particle. When a low energy electromagnetic wave is incident on it, the oscillating electric field forces the charged particle to oscillate with it. An alternating current has been induced in the wire, with a frequency equal to that of the incident EM radiation. So, first of all, we come across infrared radiation, but we already have a problem. So we can direct the infrared radiation from part of the sky onto our detector using the large millimetre telescope. While the signal does reach the detector, room temperature objects also emit strongly in the infrared, even the detector itself, so the weak signal from space is obscured by radiation from all around the detector. To solve this problem, research is being conducted into cryogenics, which is achieving extremely low temperatures in order to reduce the radiation that obscures our signal. Now, the detector itself. We use KIDs, or kinetic inductance detectors. These are an array of resonator pixels based on superconducting material, which also operate in extremely low temperatures. These resonator pixels are designed so that radiation of a specific frequency will cause resonance in each pixel. When infrared radiation of a specific frequency, for example 30 terahertz, is incident on the KIDS detector, it will cause the 30 terahertz pixel to resonate, and the output electrical signal will show that this frequency radiation is present. We have now unlocked detection of interstellar dust and gas. The dust contains around half of the heavy metals in the universe, and it is what stars are formed of. From this, we can learn more about the interactions which have taken place between galaxies and their evolution. We can also see stars which are forming within nebulae, as the optical light can't pass through the thick dust and gas. Now, moving on to the microwave region, there can't be much matter in space which is colder than dust. But there's something of major importance to be found in this region. The cosmic microwave background. This is evidence for the Big Bang theory. The cosmic microwave background was first thought to be constant noise, but it was found to be completely uniform radiation from every point in the universe. The different colours here indicate tiny differences in frequency of detected radiation. When this radiation was first produced, it was from a higher frequency part of the spectrum, but we detect it in the low frequency region because it has been redshifted, essentially stretched by the expansion of the universe to the low frequency radiation we now observe. So now we have unlocked this region onto the low energy of radio waves. To detect radio waves, we use antennas which work on the same principle discussed earlier. By this action, an alternating current is induced in the antenna. The antennas are hooked up to electronics that record the signal. Often they have to be modulated as the electronics can't cope with the low frequencies. When we use these to observe the skies, we unlock synchrotron radiation. Note that this is not from thermal radiation, but from fast-moving charged particles that pass through strong magnetic fields in space. Therefore, this tells us about the magnetic field in the universe.